Okay, Year 12, the other analysis technique for inorganic molecules, and you can also use it for organic molecules too. These two that we've grouped together, colorimetry and UV visible spectrophotometry. So, like AAS, it's looking at absorption of light by a sample, and absorption being proportional to concentration of your sample. Okay, so here with colorimetry and UV vis, we're looking at ultraviolet and visible being absorbed by our samples. Okay, AAS, we're looking at in the gaseous phase. Here we're looking at usually stuff in solution. Okay, so this is really good for stuff in solution, and it's good for other things that AAS won't do. It can do some of those metals, but it's mainly for organic molecules and other stuff. Okay, it's a bit broad, a terrible description, isn't it? Okay, so it uses light absorption like AAS to determine the concentration of some inorganics in solution. Okay, colorimetry uses the same idea, but it only gives out set wavelengths of light, only 3 or 4 wavelengths. So for example, the one that we've got at school gives out only 4 wavelengths. These 4 here in nanometers: 430, 470, 565, and 635. So it can only produce a set number of wavelengths. It's only got a set number of diodes in there probably. And so it just produces that light and looks at the light intensity going into a sample compared to the light intensity coming out of a sample, because some of it would have been absorbed, and doing the calculation. So that's a colorimeter. It's limited to the light that's coming through, only a few set wavelengths. UV vis spectrophotometry, though, so using a UV vis spectrophotometer, offers all of the wavelengths. Okay, it can scan all of the wavelengths and measure the change in absorption with the change of wavelength. Okay, a colorimeter can just measure absorption at certain wavelengths. UV vis can measure absorption at all wavelengths in its range. Okay, usually from 100 to 700 nanometers. Okay, all right. So that's the difference. That's why I kind of grouped them together. There's not much difference. They work on the same principles. Colorimetry is just defined wavelengths. UV vis spectrophotometer is looking at absorption for all the wavelengths. Okay, so here's like a representation of a colorimeter. You've got, this is the one that we've got at school there. So you've got a little slot to put your sample in, and it closes up and it shines a bit of light through there. Okay, and it measures the initial intensity versus the final intensity coming through. Okay, so it looks at how much is absorbed. And if you look on the top here, and we'll look at the one at school, there are 4 dots. These are the 4 wavelengths that you can set it at. Okay, and so here's like a cross section just above. There's a bulb that's shooting out light. So our initial intensity, it shoots it, some gets absorbed by our sample here in blue, and here is the final intensity there, which is less than the initial intensity. So it does the calculation, which is the log to base 10 of, I think that one. I might have that around the wrong way. But it does that, the log of that, and it gives you an absorbance value. So it gives you one reading there. Okay. All right. I think I've done good there. Let's look. Oh, okay. So if you've got an unknown sample that you want to find a concentration of, just like in AAS, you'll make a series of dilutions that have known concentrations within a certain range. Okay. So here they've used the pink ones. I've just used the images from before. We do a series of standards, then we do a calibration curve, and then we do our unknown and see where it fits in the calibration curve. So processing the data is exactly the same as AAS processing the data. Building a calibration curve, concentration versus absorption, finding the linear trend, and then mapping your unknowns to that. Okay. So remember that high absorption means a low amount of light made it through to the other end, and low absorption means that most of the light made it through the other end. Okay. All right. As I was just saying, you'll make a concentration curve, measure those absorbances, you'll find the linear trend, and then you'll get your unknown and put that in. Okay. So the same processing as AAS. All right, let's look at the how a spectrophotometer works, a UV vis, so the whole thing that can measure all the wavelengths. Okay, so it doesn't just scan at those certain wavelengths; it can produce light at any of the wavelengths between 100 and 700 nanometers from memory. Okay, it does not have set wavelengths, although you can set it as if you want. You can just set it to one wavelength and measure absorption and use it like a colorimeter, okay? But you can also set it to measure the absorbance for all the wavelengths. Okay, oh, that's what I was just saying here. Two types of outputs. It can produce a wavelength versus absorption graph, which we'll look at, and we can call these UV vis spectrograph. Or it can be used just like a colorimeter. One wavelength, give me the absorbance, okay? So this is what they look like, usually these days. It looks like a big colorimeter. You put your samples in here, you put the lid down to block all light, and it will give you an absorbance like a colorimeter, or you can connect it up to a computer, and you'll get a wavelength versus absorbance readout, okay? So you could get a spectrograph, or you could just get absorption. You can set it to either, whatever you want to do there, okay? The sample, your aqueous sample, or it could be something else, but a liquid sample is put into one of these, I was going to say cubes, but it's not, it's a square prism kind of thing. They're called a cuvette, okay? All right, so let's talk through how this works. All right, I like this diagram better. Okay, I'll constantly go back to it. It's better, it's got pictures, I love pictures. Okay, so first up, we've got the light source, okay? We've got two globes in there. We've got one that we're pretty familiar with. We've got a lamp made from a tungsten filament. That's just an old school incandescent bulb, tungsten filament. So those old school incandescent tungsten bulbs produce a wide range of frequencies, a nice even one throughout the visible spectrum, okay? So that tungsten lamp is giving us pretty much all of that, okay? So all the colors that we see. That's why when we turn the light on, it appears white, okay? Because it's the mixture of all the visible colors. The deuterium lamp, remember deuterium is H2, okay, so it's got a lamp with deuterium in there, so there's a second bulb, and it's producing the 190 to 400 range, okay, so a little bit above here, not the full ultraviolet range, so it's providing all that ultraviolet light there, which to the visible eye we can't see, okay, so two lamps in there, let's see on our diagram, yeah, here we go, a D2 lamp or I'm going to say H2, a deuterium lamp, and our tungsten lamp, okay, depending on what wavelength we'll want. Okay, from there it goes to a monochromator, and remember that from AAS, it's like a prism that spreads out the light, but it's like a CD disc, okay? It's microscopically got a ridged surface very regular, and it splits apart the sunlight into its component wavelengths, okay? So, rotating this grating, if you alter the angle for it and you have a slit down here, what you can do is just focus in on one wavelength. So look at this, how they've got all the colors of the rainbow. This is tilted, so only that green wavelength makes it through that slit and into our sample, okay? And this will tilt over time, so then at a certain time, then the yellow will come through, then the red will come through, okay? So that's how we provide one wavelength at a time, by tilting that through a slit, okay? How have they done it in the diagram here? Yeah, there we go, monochromator, okay. Okay, from here, what we have is like a prism where the beam is split. Okay, it's split two ways. So light comes in all together and it's half split down there. So the same wavelength ranges, just half the light goes one way, half the light goes the other way. Okay, it's going to deliver to these two samples, the reference and the sample cell. Okay. Dual path, dual meaning two, UV vis spectrometers split their light path and send light through two samples. One sample contains what we're trying to measure the absorbance through, so our sample, and the contrast, our reference one. The aim is to have everything in there but what we're looking for. Okay, so if you had, say, you were analyzing for iron 2 plus in there, and it was dissolved in water, what you'd have in the other sample was you'd have a cuvette with the same water that you dissolved the iron into, but hopefully no iron there. So that's a reference, okay? So that's aiming for to get rid of if the water or the solvent or anything else in there is going to absorb the same light as well. Okay, so it's a reference cell. So the aim is that the difference between the reference and the sample is just the analyte you're looking for. Okay. All right. So the cuvette I talked about earlier. So common. Oh, I drew a circle. Distraction. Commonly made of plastic for us. Okay, and usually at university too. More expensive ones are made of silica glass. Very expensive. I remember that using those a few times, and I think it was like $500 for one of them. And yes, I was very careful. The difference is that the clarity, how much light is transmitted through that clear surface, is much more for the more expensive it is. The plastic ones, though, for most activities that we'll ever do and just learning stuff, it's good enough. There's no real difference. Okay, down the other end, we've just got a detector, the light detector that picks up how much light came through the sample. And it also does the maths of minusing away the reference absorption as well. So it does the maths between, hey, what's the difference in absorption between the reference and the sample? Then it either sends the data to, if you're just measuring one absorption at one wavelength, it just puts a number up on the screen on the UV vis. So it just goes absorbance equals 0.890, for example. Or it sends it to a computer where you have where you do a scan of all the wavelengths and you get a spectrograph out of it. And here's the spectrograph. It's a complex spectrograph. It's multiple spectrographs all in one. Okay. So don't freak out. So a UV vis spectrograph is one of the two outputs that can be given. It's a wavelength versus absorbance graph. So absorbance and Y, and it's a range of wavelengths. So it's measured the absorbance of your sample through different light, different colored light. High absorbance means that wavelength that was shining light through, light didn't make it through the sample very well. Low absorbance mean that pretty much all the light went through. Okay, so here is multiple of them. Okay, and so each one of these lines, if I change to orange and trace that top one, here's the absorbance at certain wavelengths of a sample. Okay, you can see down at 200 it's got a medium absorbance and it slightly went up and then down, and then it had a few little peaks. And between just less than 400 here, it had pretty much no absorbance, but then it had a decent absorbance up around in the 500s and then dropped back down to 0 at 600. Now what they've done is, if you look on this graph, that's at 25 micromoles per litre, micromolar, that's the mu molar. What they've done is they've changed the concentration. Okay, so they've done the spectrographs at different concentrations, and you can see as the concentration decreases, the absorbance decreases too. So it's proportional. So absorbance is proportional to concentration, and that's really handy. Let's get rid of my scribbles here. Hopefully I go on to it. I might take us on a do-do-do. Okay, so ideally, if you measure, if you get this spectrograph and you see it's like that, if you just want to quickly use it as a colorimeter now, what I'd do is I'd go, well, what is this really good peak here that shows a really good linear trend between concentration and absorbance? And I'd look it up and I'd zoom in and I'd go, oh, look, that's 562.0 nanometers. Okay, well, what I'm going to do is, to save time in doing this for my lot of samples that I'm trying to work out the concentration for, I'm going to use my UV-Vis spectrometer as a colorimeter, and I'm going to set it to 562.0 nanometers, and I'm just going to get absorbance values out of it, just to save time. Okay, I'm not going to measure all of this. Once I know I've got this nice peak that I can just zero in on. Okay, so these peaks, where they occur, it's not really predictable. And this is a bit with a lot of knowledge, but that's way beyond us, okay? So, but, well, let's put it this way. It is way beyond us, but the NASA has decided that they're going to put this information in our data sheet, okay? So eventually, I think there might have been a question in last year's HSC, but they're going to bring it up, aren't they? Okay, so they're saying here, it's a list of chromophores versus our lambda for wavelength in nanometers. What they're saying is, if you have a sample that has a compound with a carbon-hydrogen bond, you'll see a peak at 122 nanometers. If you have a compound with a carbon-carbon bond, you'll see a peak at 135 nanometers, and so on for all of these ones. Look at this triple bond carbon-carbon, you'll see these 4 peaks, okay? So you can use the peaks in a spectrograph to kind of predict what is in the molecule, and that's what I'm thinking that they're trying to ask you in the HSC questions by putting in this. But it is organic chemistry too, all these carbon stuff bonds, okay? So here, just to show you some difference and give you some perspective here. Here we've got wavelength versus concentration, but, wavelength versus absorption. Terrible. And we've got different compounds. We've got straight pentane, straight hexane, heptane, octane, and nonane, okay? You can see that they all have peaks that are slightly shifted, but all roughly the same at around 140 or so, okay? And they all have similar peaks because we're talking about, I'll put pink everywhere, haven't I? We're talking about this peak here, okay? So it's roughly the same, it's slightly shifted, but we're talking about, hey, I'm looking at this, and with this information from my data sheet, I know that what we're dealing with is something with a lot of carbon-to-carbon bonds. Hey, that's probably an alkane, okay? So even without knowing what they are, I'd probably go with, so scribble that out. Just between these two, I'd be like, I'm guessing that this is a homologous series of alkanes. If they were all perfectly aligned, then I know it might be one alkane with different concentrations, but here we've got some slight shifts back and forth, so I know that's a bunch of different alkanes, okay? And here I've pulled up a diagram of a bunch of different alkynes, okay? It's a homologous series again, and you can see the same distinctive peaks that are just slightly shifted in there as well. If it's an alkyne, it should have 173, 178, 170. Yeah, they're all around 170, aren't they? Okay. So that's what I'm expecting to come up in the HSC sometime because they put that on the data sheet. Okay, so different functional groups on the molecule will absorb at different wavelengths, so you can help to identify these. Here's a table from the textbook. Excuse me. You're not expected to remember. They give you this in the HSC, so you'll be maybe expected to use that. If they're expecting anything more than that, they're going to have to give you extra info in the question. Okay, so here's some of my made questions that I'm like, what could possibly be in a high HSC? So here I've got an absorbance versus a wavelength, a spectrograph, a UV vis spectrograph, yeah, because we're going through into the UV down here. It's in the UV. Okay, which of the following molecules is most likely to produce the given one? Okay, we've got a peak here, and a peak here. Okay, so that's about, is that about 210, 215? All right, around 210. And what's this one? This one's about 170. And this one here's about 120. Okay, so looking at our absorption data up here, the 120 is looking like a carbon-hydrogen bond. The 170 could be the triple bond, or it could be the carbon chloride bond. The 210, well, the only thing that's high is the carbon bromine bond. Okay? All right. So let's have a look. I'm thinking, I've left it a bit ambiguous, but I'm thinking this one's a bit lower. Anyway, I'm thinking it's like it's a double bond, 160. I think that's what I'm hinting at. Okay, is it a chloro? Well, I don't think it's a chloro because we'd see maybe one up higher. Okay. I don't think it's a chloro. I think it's a bromo, ethene or ethane. Okay. Now, do we get a peak at 135? No. We get a peak, what should be around 160. So what I'm trying to hint at is this question. It's a bromoethene. Okay. Here we go. Let's see if I did better on this one and my peaks line up. It's the same type of question. Now I've just changed the spectrograph. So let's draw our peaks. So we've got 3 peaks again. We've got this one, which is about 180, 170, 175-ish. We've got this one here, which is about 135. I'm doing terrible, aren't I? And this one, which is more like the 120. Okay, so the 120 is looking like our carbon to hydrogen. The 135 is looking like our carbon to carbon. And our 175 is looking like our carbon chloride. Okay. So there's a chlorine there. So chloroethane's good. Bromo, no. Bromo, no. Get rid of it. Chloro, we're good. We need to decide whether it's ethine or ethane. If it was ethine, we'd be seeing a lot more peaks in the way up here. We'd be seeing stuff up at 222. We'd be seeing stuff up here, but we're not. Okay, so it's not the ine, it must be the ane, and that's good because we've got the carbon-to-carbon single bond peak there. All right. Oh, I've already talked through this. Okay, so the other output given by the spectrometer is the colorimeter, and look, I've taken that peak and shown that it's proportional. Okay, so you form a calibration curve and you read it off from there. Oh, here's a little bit more detail on a calibration curve, okay, and the formula for absorbance, okay. So down here, absorbance equals log to base 10 of the original light over the final light, okay. And here we've shown something else, a bit more detail. It's equal to this symbol, which represents something, we'll get to it soon, times it by the length of light that the light passes through, okay? The light passes through a certain length, which is, in our UV vis spectrometers, is kept as a standard of 1 centimeter, okay? We use a 1 centimeter cuvette. Rarely you might get a bigger one sometimes, but they're pretty rare. Usually it's a 1 centimeter, and it's concentration. So if we keep the path lengths the same, and we ignore this other proportionality constant, it's saying that absorbance is proportional to the concentration. Okay, so on to this other thing. Okay, So our slope, our y equals mx plus b. Our y is absorbance. Our m is our gradient times the path length. So our gradient is something here. We can have all different gradients for these, times our concentration. This gradient here is a factor that we call the absorptivity. I won't go into too much about that, okay? Absorptivity. So all different compounds have a different kind of ability to absorb, okay? And it's taking into account that. And what we see is a different slope on this graph, okay? Here we've also got, if we're fitting it to a y equals mx plus b graph, here because it meets at 0, 0, we've got a b of 0. But you can have ones that go like this, okay, where they have a plus b. You still use the same method, okay? It doesn't make too much of a difference. All it means is that when you had none of your analyte in there, it was still absorbing because of something else, okay? All right. More on to this Beer's law, okay? So Beer's law is the prediction that our absorbance is proportional to concentration, okay? And let's talk a bit more about it. It states absorbance of a solution is proportional to its concentration and the length of path, the path length of light through a sample. I got it out, okay? Here I'm trying to show that to you, okay? If we have a 1 centimeter cuvette with a certain orange compound in there, okay, and let's say we had a cuvette that was double the length, 2 centimeters long, what we'd notice is there'd be double the absorption, okay, because the path length is double. So I've tried to represent that by a deeper color of orange there, showing that more light is being absorbed through there, okay? So we'd see that as a deeper color. Think about, I always like to bring this back to cordial. Think about pouring cordial into a narrow glass versus the same cordial pouring it into a wide glass. The wide glass would look like a deeper color than the thinner glass, okay? And here I'm talking about concentration. Okay, so here we've both got 1 centimeter cuvettes. The size of the cuvette hasn't changed, but what we've done is doubled the concentration. So instead of some y value, it's now 2y. Notice that the absorbance is now doubled. The absorbance was some x value here, and now we've doubled the concentration. The absorbance has doubled as well. So I've done it in the darker orange. Okay, so absorbance is equal to this epsilon value, which is got many different names. Absorbance proportionality constant. Absorptivity is sometimes a name for it too. Times it by the path length, times it by concentration. Now, you can work out because absorbance is unitless, you can work out the dimensions of absorptivity. It's the opposite to moles per liter. It's liters per mole per centimeter. But that's some really extreme stuff, okay? All right, to see them in practice, okay, other than the classroom, here's 2 good videos. From memory, this is a really good one too. I can't remember that one. That one's a really good one. All right, he shows you kind of like stuff like this. Okay, let's do a practice question. Oh, this is from the checkpoint chemistry one. I should acknowledge that. It's not a past paper. So the UV visible spectrum of the solution of a certain compound is shown below, okay? Consider the following statements about this compound and its UV visible spectrum. The amount of light absorbed by a solution of this compound depends on its concentration. Well, that is probably true, but it's not showing that here. It's just showing absorbance versus wavelength. So it's not evidence for that. The amount of light absorbed by a solution of this compound depends on the wavelengths used. So absorbance changes with wavelength. Yes, we've got the evidence here with the spectrograph. The spectrum is a result of electrons falling back from a higher to a lower electronic levels. If they go from a higher to a lower, they've got to emit that energy as light. That's emission, not absorption. So no, what happens here is electrons absorb this light and get promoted to a higher valence shell. The concentration of a solution of this compound can only be determined by the UV-vis spectroscopy at 250, so by this peak. Well, here's another distinctive peak for this compound too. You could, later on, change the concentration and measure it at that peak too, so that's a no. Oh, other questions? Well, I'm only thinking that 2 is correct. Alright, there's a worksheet there for you to do, and there's some other problems from the textbook about building calibration curves, and that's the content for this chapter. Thanks, guys.